So we got number 6. Player passes the basketball down the court for fast break, leaves the player's hands at this speed, also must have kinetic energy, and slows down to this at its highest point, but we can ignore air resistance, and they want to know how high it's above its maximum height. So, let's see. Number 6. And by them telling me to ignore air resistance, I know that any work done on it is internal to the system. All right, so we're going to have no external work here. It starts by going up. I know there's going to be PE grav. So if I add it to one side, I've got to add it to the other. There's no springs or nuclear reactions or weird monkeys in play, so no other energy that I can think of off the top of my head. So I'm going to start by giving it a whole big bunch of kinetic energy. And then gravity is going to do work on it, but that's internal work, so I'm not going to give it any external work. And I know that's going to end up with less kinetic energy than it had before because it's going slower. Told me that's the problem. And so it's all internal, so any of that work that goes away has to stay with it, and it goes, because its height increases, it goes to PE grav. So that would be a perfectly acceptable 100% Y right there. I've got my energy is shown to be conserved. Yeah. All right, so moving on from that, I would go down to my how, and I would start off with the equation that my graph just created that said P grav, and I'm going to label that T. Let's say, no, sorry. Completely started off wrong. KE, and I'm going to put a little initial on that, for that's when we started. That was the initial condition. And then that told me that it equaled KE at the end, so I'm going to call that F. Actually, let's call it T for top. Plus the PE grav at the top. That's what my graph told me. That's my relationship. And then I grab from my equation sheet that KE equals 1/2 m speed squared. PE grav equals m, g, and h. All right. What planet do you think this takes place on? Earth, because it's a basketball, and the only planet I know that has a basketball. So they could have. I don't think they did, though. I'd have to look, but I don't remember that being in any of the cargoes. So now just substituting in with those equations. And I want H by itself. So, oh look, my M's cancel out. Yay! So I guess I'll just, do a little more algebra. And then I would just substitute in. Algebra. Questions? All right, we're moving on to number 8. An airplane starts at rest at an airport runway at sea level. Oh, so it has no energy then, because not, by general kind of get along with everyone, we would take ground level or sea level as zero potential energy, and if the rest got no kinetic energy. And then they want to know, the change in mechanical energy that climbs to a cruising altitude of this and maintains a constant speed of this. And then they've asked for it in megajoules. We can always change that to joules if we don't want to use megajoules, right? So, all right, let's look at our bar graph here. So, no energy to begin with. It's asking the change in mechanical energy. So that must mean some external work is done. So I'm going to give it lots of external work. And then it's going to end up with PE grav. So I've got to have that on both sides. And let's say, I don't know, 5 kinetic energies and 4 potential energies. That would be it. And of course, so that is now what generates my equation right here, which says that the work external here is the kinetic energy plus the potential energy graph. Go to my equation sheet and grab 1/2 mv squared. Sorry, that should be a KE. And mg, the weight times the height. I know m, I know speed, I know mass, I know speed, I know what planet it's on, so I know the gravitational field strength, and I know the height. Algebra's done. Do arithmetic. Be happy. All right, number 7. Number 7. Suppose the pendulum bob in figure 1 has a mass of this and is moving to the right at point B, that's the bottom, with the speed of this. Air resistance is negligible, so no external work. Okay. What is the change in the system's gravitational potential energy when the bob reaches point A? Okay. What is the speed of the bob at point A? Okay, so A must not be all the way up. If they're asking me the questions this way, I'm going to assume it's not all the way up. All right, so they told me forget about air resistance, so that's telling me there's no external work. I know there's going to be PE grav along the way. Probably not PE spring because there's no spring in the problem. So, bunch of kinetic energy here to start with. 7 of those, 6, 7 of those. No external work. When it gets up to point A, I'm going to predict that it's going to be going slower, but it's also going to have gone upwards, so it's going to have some PE grav. But it's still going to have some kinetic energy because it hasn't reached the top. Or it's reached the top and come back down. Either way would work. Right? So we don't really care what happened in between. We care about the endpoints. Good on that one? Yeah. All right. So, KE at point B equals KE at point A plus PE grav at point A. I think I need my little diagram, like I did other times. Do I need to write down my valid equations? I'll do this. Same as the other two. Let's see. Bring it here. Bring it here. 35 degrees. 1.2 meters. 1.2 meters. That little portion in there, oops, that's a horrible H, is going to be H, the height that it goes up, right? Remember that problem we did yesterday? Did we do the pendulum one in here? Fine. You guys know what I meant. Okay. When we did example problems. So, therefore, H will equal 1.2 meters minus 1.2 meters cosine 35 degrees. A little geometry, a little trig, right? As you got a right triangle there. If you guys haven't done the exit ticket, can you start doing the exit ticket, please? I'll keep writing up here so you have it, but so you're not late to your next class. Part A. That's all.